Without further ado, let me introduce the speakers. So Morten Kringelbach is a professor of psychiatry at Oxford University and a senior research fellow at the Queen's College. He's the director of the Eudaimonia Research Group. And his research goal is to reverse engineer the human brain, in particular to elucidate the heuristics that allow us to survive and thrive. He focuses on elucidating hedonia, or pleasure, and eudaimonia, or the life well lived, and how they're affected in health and disease, in particular to elucidate their breakdown in anhedonia, or the lack of pleasure, in neuropsychiatric disorders. He's also, as far as I'm aware, the only professor of neuroscience at Oxford who is doing research on psychedelics. Andrea Luppi studied philosophy, cognitive science, and neuroscience at Oxford, and he's currently completing a PhD in clinical neuroscience at the Division of Anesthesia, University of Cambridge. His work characterizes how the capacity for cognition and consciousness arises from the complex interplay of brain structure and function. To this end, he combines multimodal neuroimaging across a variety of states of altered consciousness, such as disorders of consciousness, anesthesia, and psychedelics. And finally, last but not least, Parker Singleton is a PhD candidate and National Science Foundation Research Fellow at Cornell University in Amy Kuchieski's, I'm not sure if I'm pronouncing that correctly, computational connectomics lab. He's studying the effects that potent serotonergic compounds have on brain activity and connectivity, and pursues the development of computational models to drive targeted brain therapies. He hopes his research can be used to inform theories of consciousness and to better understand, diagnose, and treat mental disorders. So we're going to have a 20-minute presentation from each of the speakers, followed by some Q&A with the audience.
So let's get started. So thank you. Yeah, it's a great pleasure to be here and to be talking to you about some of the work that we've been doing before and during the pandemic. So let's dive right in. Like Morten and like Parker, we are interested in consciousness. And some people might think that that is almost paradoxical, because William James famously described consciousness as the flights and perchings of a bird. It's always changing, always flowing. So hopefully, though, what Morten and Parker will be able together to convince you is that we can actually make progress into the scientific study of consciousness, so that we are not stuck in the situation that is described here. We can actually make scientific insights tangible. And in particular, there is one very interesting problem that all of us are going to be touching on in different ways, which is that even though we have these very many and very different kinds of mental states that we go through over the course of a day, but also even over the course of an hour, sometimes over a few minutes, the structure of the brain is always the same, changes much more slowly than our mental states do. And one way that we can try to get some insight into that is by thinking not in terms of mental states, but in terms of brain states. So what kind of brain state corresponds to a particular mental state? And how does the structure of the brain support the various flow between these different brain states? And you might think that this is a very abstract question and that we don't even have a frame of reference for thinking about it. But I would argue that actually we all do, because all of us, unluckily, are familiar with the question of traffic. And we can think of the roads between different cities or between different parts of a city as a structure. And what happens is that we can then think of the traffic as the function that is taking place over it. And as a result, we can ask the question of how much function relates to structure. How much does the presence of roads between two places predict the presence of traffic between them? And we know that that is changeable over time, because sometimes, for instance, during weekdays, there is going to be a lot of traffic on the bigger roads. But during weekends, even if a road is particularly big, it doesn't mean that there's going to be a lot of traffic over there. And this is a way that we can think of relating structure and function, by thinking in terms of the network of roads and the interactions that occur over this network. And of course, that is exactly how we think of the human brain. So if we think of different brain regions as different cities, then we can take the physical connections between those brain regions, between those cities, as our structural network, our structural underpinnings. And that is basically the roadmap onto which brain activity interacts, so that different brain regions can talk to each other. And of course, as a result, we can think of brain activity as the flow of traffic. And once we have this framework in place, we are now in a position to investigate how brain structure relates to brain function. However, there is one ingredient that is still missing, which is, do we have a rigorous mathematical framework to relate these? And as I'm going to show you in just a moment, we actually do. So you might be wondering, why did I show this video? But hopefully we can clarify that right now, which is that, what is this video actually showing? It's showing sand over a metal plate. And that metal plate is being made to vibrate at specific frequencies. And as this slide here shows, depending on the frequency, the sand over the metal plate takes on different configurations. And these configurations are not random, as one might perhaps expect, but rather, on the contrary, they have a lot of architecture in them. And that architecture is dependent on the frequency. So this is a way that we can think of structure, that is the metal plate, relating to function, that is the configuration of the sand, in a way that can change over time and can be modulated, in this case, by the frequency of vibration. And of course, the reason why we care is that this is not just something that happens with sand over metal plates. It is not something so abstract, but rather this is the same principle that we use to make music, as you can see in this figure here, where different frequencies elicit different kinds of vibrations over the body of a musical instrument. And in fact, this is also the way that different animals get their specific patterns over their coats. And the important thing is that if instead of a metal plate or a musical instrument, we use as our structure the structure of the human brain, or as it is sometimes called, the connectome, then what we can get is patterns not of sand over a metal plate, but of activity over brain structure, which is what you look at right here. And hopefully you can appreciate that there is a remarkable analogy between these patterns of activity over the brain and these patterns of sand organizing over a metal plate. And this is not something that happens randomly, but rather the reason why there is this underlying fundamental similarity is because the mathematics that organizes activity over the brain or sand over a metal plate is the same, and it is the mathematics of harmonic modes. And hopefully you can see here that these patterns of activity over the brain are not just organized in terms of different symmetries, but they're also organized in terms of different granularity, or as we call it, spatial frequency. And this was shown by Selen Atasoy from Morten's group a few years back with this beautiful paper that was showing how different spatial frequencies correspond to different patterns of activity over the brain, which you can obtain and you can predict from the organization of the brain's structural network. And the way that I think about this is that you can use this connectome harmonic decomposition, which is the term that Selen Atasoy coined. You can use it to understand how brain activity can be broken down into these fundamental patterns that arise from the structure of the human connectome. And there is a mathematical formulation of this, which would be to say that this is equivalent of applying the Fourier transform over a graph. But because I am not a native speaker of math, I find that there is an analogy that is very helpful in terms of understanding what this decomposition is about, which is thinking in terms of smoothies. Now, you might imagine that you have two different smoothies, and you know that the ingredients that went into each of these smoothies are the same, these pieces of fruit represented here, but their relative prevalence is different. And in particular, the top smoothie included a lot more strawberry, a lot more watermelon, and as a result, its color is primarily red. Whereas if you have more mango and more orange, you're going to get a more orange smoothie. And this is, in some sense, the same principle that we are applying when we apply connectome harmonic decomposition. We have a set of ingredients, which are these mathematically derived universal patterns of activity obtained from the structural connectome, and we are relating them in order to understand how a particular brain state, which we think corresponds to a particular mental state, arises. And this is exactly the framework that Selen and Morten and their collaborators applied to understand the effect of psychedelics. And in particular, their first paper, this paper in Scientific Reports from 2017, was able to show that there is a beautiful signature that you observe in terms of these connectome harmonics when you compare people who are under LSD to people who are under the effects of a placebo. And this signature can be best seen in terms of this energy, which is a term borrowed from physics that corresponds to the contribution of each of these harmonics. And as you can see here, there is a very clear pattern whereby the low frequency harmonics, so the ones with more coarse-grained patterns, become reduced when someone is under the effects of LSD. And instead, the high frequency harmonics, so the patterns that are more diverse, more fine-grained, more complex, those patterns become increased under the effects of LSD. And of course, I should clarify that all of this was obtained from functional MRI, which is non-invasive measurements. And these are the same LSD data that we've seen before in Morten's talk, kindly provided by the lab of Dr. Robin Carrar-Harris. But of course, Morten and Selen did not stop there, but rather they were able to generalize this signature not just to LSD, but rather to other serotonergic psychedelics, namely psilocybin, the main active ingredient of magic mushrooms. So in this follow-up work from 2018, they showed that the same exact signature can be observed not just in LSD, but also in psilocybin. And in fact, there is some more recent work by my collaborator, Morten's student, Jakub Vorizek, showing that even DMT will show a very similar profile. So my work came in about the beginning of the pandemic, showing that the same signature, or a very similar one, can be observed also with ketamine. Now, the reason I was especially interested in ketamine is because unlike LSD, DMT, or psilocybin, ketamine is not a serotonergic psychedelic. It's not an agonist of the 2A receptor, but rather it has very different molecular mechanisms of action. It is what is called an atypical psychedelic, which means that it has psychedelic-like subjective effects, but very different molecular mechanisms that make it not a classic psychedelic. In fact, at high doses, ketamine is known as a dissociative anesthetic. But here we used sub-anesthetic doses, which are known to have psychedelic-like effects. And we were able to show that indeed we find similar results in terms of this connectome harmonic signature with elevated presence of these high-frequency harmonics. And remarkably, we were also able to show that exactly the opposite signature is observed when we compare wakefulness with anesthesia induced by the anesthetic propofol. So in this case, we see less contribution of the high-frequency harmonics and more contribution of the low-frequency harmonics. And you can find all of this work in a preprint that is on bioRxiv, that is the result of our collaboration together. And even more interesting, we show that this same signature of unconsciousness can also be observed not just during anesthesia, which is like psychedelics, a temporary condition, but also in disorders of consciousness, which are unfortunately in most cases permanent and which arise not from pharmacology, but rather from severe brain injury of different kinds. And regardless of how this brain injury came to be, we see that the same signature characterizes both unconsciousness induced by anesthesia and unconsciousness induced by a disorder of consciousness. And of course, this is the opposite signature of what we have observed before with the various psychedelics. And this lets us conclude that these signatures pertain to the actual mental states that we're interested in, rather than being due to a particular way to get to that mental state, whether that's a particular kind of psychedelic or a particular kind of anesthetic or a particular kind of brain injury. So going towards the conclusion, what we can see is that these connectome harmonics let us obtain what we can call a multidimensional signature of the psychedelic state, which includes lower contribution of the low frequency harmonics and higher contribution of the high frequency harmonics, and which is the opposite of the connectome harmonic signature observed from anesthesia or from a disorder of consciousness, which is to say the signature of unconsciousness, if you will. And we can actually go even a little bit further to show that if you plot them on a one-dimensional scale, you will see on one end of the scale that there is a reduced complexity of the signature when it comes to loss of consciousness, whether induced by anesthesia or by a disorder of consciousness. And instead, there is an increased complexity of the signature, which is induced by ketamine or by LSD. So different kinds of psychedelics corresponding to the more diverse set of experiences that one undergoes, and supporting the entropic brain hypothesis of Robin Carhart-Harris, which you will hear more in Parker's talk. So finally, the way that we can read this map of connectome harmonics is that the low frequency harmonics are effectively corresponding to structurally coupled patterns of activity, whereas the high frequency harmonics correspond to structurally decoupled patterns of activity. And once we put them together, we find that anesthesia and disorders of consciousness are in general more structurally coupled, as we obtain from this signature, whereas LSD and other psychedelics are more structurally decoupled. And all of these results have also been corroborated by previous work from myself and from others. So we are getting towards a robust characterization of what it is that disorders of consciousness and loss of consciousness differ from the various psychedelics. And this is about the mental states. It's not about the particular way that you get there. So hopefully I've been able to convince you that these particular signatures of the various mental states that we have can be obtained with this very powerful framework of connectome harmonics. So that connectome harmonics, because of the underlying fundamental mathematics on which they rely, can act as a compass, if you will, to navigate and map this complex landscape of consciousness. And there is a lot more work to be done, and some of it is being done by Selen Atasoy, Jakub Forizek, and others. And speaking of Selen and Jakub, all of them have contributed greatly to this work. So this is by no means my own work, but rather Morten contributed to this, Selen contributed to this, Jakub contributed to this. And then of course we have the people who provided data, like Robin Carhart-Harris and Leo Roseman, but also the people who provided data for the disorders of consciousness, for the anesthesia. And finally, I should also thank my supervisors, Dr. Stamatakis and Professor David Menon, for their support throughout my PhD. And I look forward to your questions later on. Thanks for your attention.
Amazing, Andrea. Thank you so much. That was a fantastic presentation. And last but not least, Parker Singleton.
Okay. Yeah, thank you for having me here today or tonight for you guys. I'm really thrilled to present alongside Andrea and Morten. The work that I'm going to show is actually done in collaboration with Andrea and Morten, and again, data provided by the generous group at Imperial College London with Robin Carhart-Harris. So I'm going to talk a little about some evidence that we provide for a flattened energy landscape under psychedelics. But before we really get into that, I want to just kind of talk about the idea of an energy landscape and what we mean conceptually by that. So here I'm showing you a steep geographical landscape, and we have water flowing through this landscape. And because it's steep, how the water flows is sort of forced into these low energy valleys, and it's surrounded by these high energy mountains on each side. And because of these high energy valleys, the water, the path through which the water flows here is not going to change much over time. There might be small changes over long periods of time due to erosion. A new bend might be formed here or there. Maybe there's an avalanche that changes the path slightly. But all in all, compared to what I'm going to show you next, this is a pretty static landscape. and there's not much entropy, if you will, here. So if we look at a very flat landscape, this is one commonly observed in the coastal regions of the southeastern United States, where the flow of water here is driven more by tidal fluctuations than change in elevation. So if you look at these tidal creeks, you see the water is taking this very meandering and random route. And it would be kind of hard to predict where it's going. If you were kayaking in this environment, you might get lost pretty easily. And I'd also like to point out that this type of landscape is very dynamic in terms of where the water flows. It changes on much shorter timescales than, say, the steep landscape on the left. So something like the size of a football pitch, and the area of a football pitch is eroded and deposited in different locations in just the Louisiana Bayou every day. So this type of landscape's dynamic and changing, and where the water flows is in some ways unpredictable, or less predictable at least. And so I'm sure a lot of you, since this is the Psychedelic Society, have heard of Rebus. I'm just going to briefly introduce it again here. So, Rebus takes the idea that the brain is a prediction engine it's basically a physical model of your universe, and it takes incoming information, and based off of prior experience, it makes predictions about the world around you. And in Rebus, the brain organization here, or the models organization under psychopathology, is such that you have these pathologically overweighted priors coming from the upper levels of the hierarchy, shown here by this thick top-down arrow. And the result is that a suppression and a insensitivity to bottom-up information that's maybe intrinsic to the system from like limbic areas or even sensory areas for external information coming in as well. And the result of these overweighted priors is a pathologically like rigid or frozen system that is relatively insensitive to perturbation. And so if you think about it, this is really kind of the case of what's going on in these treatment-resistant pathologies, where patient outcomes are not responding to conventional therapies. And so they propose that brain organization under psychedelics is such that these top-down priors are de-weighted, shown here by now a translucent arrow, and the result is a liberation of bottom-up information from limbic and sensory regions. And this system is now like maximally sensitized to new information. And the effect of de-weighting these priors is thought to also result in a reduction of the curvature of the free energy landscape that holds the patterns of neuronal dynamics of the brain. So you flatten out this energy landscape, and now two things might potentially happen. Not only are there maybe more neuronal patterns accessible due to a flattened landscape with lower transition energies, but also you might be switching between these different patterns of neuronal dynamics faster because the wells aren't as deep and the barriers aren't as high. So there's just less energy to move from one state to another. And so that latter part of Rebus was what we wanted to test here. Basically, do psychedelics reduce the energy required to transition between different brain states? And we used some new tools, or actually very old tools from network science, but only recently have they been applied to the brain. This is network control theory, and this illustration that I'm going to provide here is with transportation again, just as Andrea provided. And think about what he said, because he said it better than I can, and this is going to be like really, a good illustration, or a synergistic illustration, I guess, So if we look at this map of the US road system, you see the blue lines are connecting different cities, and you can already kind of, well, actually cities aren't even on this map, but you can kind of guess where they might be just based off of where a lot of blue lines are coming together. And so if we pick a few of these kind of hub regions where a bunch of roadways are coming together, we'll call those nodes in our network. And then we're going to create this network by connecting these nodes based off of, let's just say, how many lanes of highway are connecting each region. And so I'm showing here, now we have a network, and the thickness of these lines is arbitrarily based off of how well connected they are by highway. And I totally arbitrarily put these weighted lines in. So if they're not adding up completely with the map, just ignore that. So that was our network. And now we're going to define like a state in that network as, based off of nodal population of people. So Andrea talked about, structural connectivity networks like roadways and traffic, like the activity or the people moving from one place to another. So we're doing the same thing here. I'm just illustrating different states on this network. So yellow on a node is going to correspond to a lot of people at this node at a given time, and blue is just relatively less people. And let's say this is like this is like early morning, everyone's at home, and like rush hour traffic hits and people commute to work like they used to in the old days. And so now we have the same network, the same connectivity, because the roads don't change at 9 a.m. But what changes is where the people are or where they're trying to get to. And so what network control theory allows us to do is to understand how the structural connectivity of the network facilitates this flow of people from a set of nodes to another set of nodes, and also quantify the energy required to move people through that network. So you could obviously think about the practical applications of this type of science with designing new roads for traffic migration, or it's also been used in like the electrical grid, based off of just different temporal demands and where you need to route information or people, or in our case, brain activity. So we'll take that same network and we're just going to apply it now to a brain, where again, like Andrea said, cities are now different parts of the brain. Instead of people, we're talking about activity in those parts of the brain at each node, based off of or measured by functional MRI. And the connectivity of these different nodes is defined by the structural connectivity, the white matter tracts of the brain. And so we use this to, we have different brain activation patterns measured by fMRI, and we're going to use network control theory to quantify the energy required to transition between the states. So again, got those roadways, structural connectivity. We're talking about the white matter connectivity that connects different parts of the brain. And you can think about these activities, these brain states, as just different activity patterns. And again, like Andrea mentioned, the structural connectivity is like very static, just like your roadways. They don't change very much, or at least not over short periods of time. And what we're studying is how those roadways or the white matter facilitate these functional brain activity states, where the brain activity is moving through this network from one pattern to another. So I'm going to present like the first set of results with Lsd data set from Robin Carhart Harris. And just as like a little aside, like a lot of this was replicated with psilocybin data set as well. I might not go through all of those though. But to give you an idea, we've got the LSD and the placebo sessions that were recorded with fMRI. And we use a clustering algorithm just to identify common brain activity patterns that were visited by these subjects at each time point. And then we'll use network control theory to just study the energetic demands between these different states in each condition. So I'm showing you the 4 states at the top. They're labeled based off of some resting state networks, but you don't have to worry about that. You can just think of them as state 1, 2, 3, and 4. And so we use network control theory to measure or to quantify the energy required to transition between each pair of these states under LSD and under placebo. And comparing those energetic demands, we find that the LSD energy landscape was significantly reduced in every possible transition. We wanted to go a step further with this and ask a little about the mechanism by which these transition energies are decreased by LSD. And one of the things allowed to you by network control theory is to study the impact of giving certain nodes in your network more control over other nodes. So kind of by default, what we did on the previous slide is you give every region uniform weight or uniform control over the transitions. But we know that LSD and psilocybin bind to the serotonin 2A receptor. And so we can obtain a weighted distribution of that receptor in the brain using PET imaging. And we hypothesized that if we skew control in our model based off of nodal density of the 2A receptor, that would also result in a reduction of the transition energy, similar to what we observed when people were actually given the psychedelic. And that was indeed what we observed. And we also wanted to test the spatial specificity of this finding of this 2A map. So we like did a couple of things. We randomly shuffled these values, and we did that 10,000 times, and we recalculate the energy landscape every time. And we found that the true distribution of 2A in the brain was always lower than this randomly shuffled 2A distribution. So that tells us a little that there's it's not just the values themselves, but also where they are in the brain that help facilitate this reduction in energy. This is a little more technical, but we also, instead of randomly shuffling those values, we spin them along the cortex. The result is that you keep basically the neighboring values are all the same. So you have these spatial autocorrelations of the values that are preserved, but we just put them in a different spot on the cortex. And that also resulted in, well, we saw the true distribution, the unspun distribution resulted in a lower energy landscape than the spun distributions. We also did this same idea with different serotonin receptors, hypothesizing that the 2A receptor would be the most effective at flattening the landscape. And we show here that was the case. It's got the lowest set of energy values. And interestingly, the 1B receptor was like second lowest. And that receptor is coming up a lot lately as a potential site for the antidepressive effects of SSRIs, as well as potential site for the synaptogenesis effects of psychedelics. We know 2A to be very responsible for the subjective effects, but when we block, that receptor has been blocked in humans and in rodents, and those effects go away. And in rodents, we see the synaptogenesis effects that are presumably mediated by maybe 1B. So it's interesting that that's the second most effective at lowering the energy. We also saw that how much the energy was lowered by LSD correlated with more dynamic brain activity on an individual level. So here on the left, I'm showing you correlation between energy reduction by LSD and also reduction of the average dwell time of these 4 states. So we can measure dwell times anytime a person visits a state. We can see how long they stay there. And that tells us, a little bit about the dynamics of these people. So under LSD, or the more energy was reduced, we found the more the average dwell time of these states was reduced. And then correspondingly on the right, we're showing that energy reduction by LSD also correlated with an increase in the average appearance rate, or just think of it as the number of times people are switching between states per minute. So all that to say that the more energy is reduced by LSD, the more people are like switching between states. And lastly, you can imagine that you can imagine a scenario where people are switching between states more often, but that sequence of states could still be highly predictable. For example, 1, 2, 1, 2, 1, 2, 1, 2, just on and on forever. There'd be like no complexity or entropy in that. But so we wanted to test, was energy reduction by LSD also correlating with complexity or entropy of these sequences of brain states that were visited, and we found that was the case as well. So we repeated, so all those results were shown with LSD. We repeat them very robustly with the psilocybin data set. But there's this one thing where the LSD and the psilocybin data sets were different that I think is quite interesting. And so, and I'm going to propose that maybe it has something to do with how the data was collected for the two studies. So under the LSD data set was the functional MRI scans took place about 2 hours after LSD administration, in which they were trying to measure the peak effects of the psychedelic. And the psilocybin data set was recorded actually immediately after infusion of the drug. So the patients were in the scanner before infusion, during, and after infusion. And so we're, you know, I would think that we might be looking at two different windows of the psychedelic experience, perhaps. So with the psilocybin or with the LSD data set, even though we show some group level differences in dwell times and appearance rates of individual states, when we look at just the average dwell times or the average appearance rates over all the states, we don't see any group differences. And that's, you know, kind of not what we expected, because we would expect that when you reduce or flatten that landscape, you have lower energy barriers, there's going to be just more switching. And we show that amount of reduction correlated on the individual level on the previous slides, but we didn't find actually group level differences. However, with the psilocybin data, we do find very strong group level differences between that average dwell time and the average appearance rate. And you know, I think this is quite interesting. I know I heard at one of your previous symposia with DMT, some people were talking about consensus reality space, and potentially under the DMT experience, you at some point when you break through, you're in this like different state space, but one that's more stable. And you know, I'm just kind of throwing it out there that, you know, maybe we're looking at just different, the dynamics at the very beginning of a psychedelic experience may be different than the peak effects. Maybe the peak effects are you know, capturing just something more stable in the state space. I don't know. Our lab's also showing that pathologies are associated with increased transition energies. And so, you know, providing potentially an idea of some clinical applications where under pathology, you have increased energetic demands to transition between states, and maybe psychedelics can help reduce those energetic demands and facilitate recovery. So in summary, psychedelics reduce transition energies between states. The 2A receptor specifically demonstrates, or the 2A receptor is specifically important as demonstrated by our model. We also show energy reduction correlating with increased entropy of brain dynamics. We're showing pathology is associated with increased transition energies. And all of this is in support of the Rebus hypothesis. You can find our preprint with Andrea and Morten on bioRxiv. You know, this is the whole team that was involved, and we're, you know, I'm super thrilled to work with such wonderful people. And also shout out to my advisor, Amy Kusieski, who, you know, this couldn't have been done without so many people, including Robin and Andrea and Morten and Amy. So quite thrilled to be here and present it with you today. and funders and stuff. So I think I'll stop there. Thanks.
Awesome. Thank you so much, Parker. Another really incredible presentation. So we've got about 20 minutes for Q&A. So I'll ask each of the speakers to just try to be as brief as possible so we can get through as many questions as we can. We've got quite a few on the Zoom chat. So I'll start with a very general question, which is there are a lot of different ideas that were presented in these three talks, a lot of different fantastic visuals. I'm wondering, since you've all worked together, what you guys think is the underlying principle that might unify all these different frameworks together, if any?
I love the way you start with an easy question, yes? So there are very strong links between each of these theories. I mean, mathematically, you can show that turbulence and harmonics are very tightly bound together. And really, the kind of control theory that Parker spoke about, of course, is also very closely linked. The big question and the big unanswered question, which I hope I brought out in my talk, is what is the best way of defining hierarchy? So in the original formulation of the rebus, it was all about free energy, right? What is free energy? Can one in a Bayesian framework really estimate that? I think the answer probably is no. And so what are the other possibilities of actually defining that? And I think what we produced is different kind of sides to describing this really interesting change in energy in the brain over time. But I mean, let's hear what Andrea and Parker thinks about that.
Well, I have a background in philosophy, so of course I'm mandated to say that the answer is it depends. But leaving that it depends aside, I think what we have been, all of us have been showing in different ways. And of course you will notice that there is a common denominator to these three talks, and that common denominator is Morten, really, and his work. But I think in all of them comes the question of brain structure and function. We've been using different ways to look at brain function. We've been using different ways to look at brain structure. But in all of these cases, there is, which is the theme of this workshop, really, the flow of brain activity and how brain structure constrains it, and how the neurobiology of the brain interacts with the structure to generate these different kinds of patterns of activity. And in some sense, what we have been doing throughout is just using different kinds of mathematics, which, as Morten said, are closely linked to each other, to try and get a sense for how the neurobiology on one end, whether that be through perturbations, different kinds of pharmacology, and the structure on the other, together orchestrate the emergence of these patterns. And I think it is exactly as Morten was saying earlier, there is a lot more work to be done, but I think this is a very exciting time to be doing this kind of work, because all of these ideas are starting to come together and be bound together. And we're starting to have the conceptual frameworks to bring them together and the mathematical tools to make actual progress on there and go, as I was mentioning earlier, from maths to science. And I think this is what's making this such an exciting time.
I don't have anything to add to that. Beautifully said by both Morten and Andrea.
Amazing. Let's move on to questions from the audience then. I will start with Eva. What can a model of human consciousness based on turbulence show that other models cannot? And what are the main shortcomings of other models that turbulence can address? So this is a question mostly for Morten.
I think it's a very interesting and of course very deep question. It shouldn't have come as a surprise to us when we discovered that there is turbulence in brain dynamics, and yet nobody else had thought to look at that. When you think about how many other phenomena are really well described by turbulence, it shouldn't have come as a surprise. Now, the key thing, as I say, that is probably the most important factor of turbulence is this ability to basically mix information across different scales. And so it's a fundamental principle, not just of brain function, but of all things that, as I work here, but what is really special about the human brain is that the brain has a certain structure, as Andrea and Parker also pointed out. And there is something about that particular structure which is perhaps unique in the universe, in that we have these very interesting connectivity patterns, which can be abstracted down to this idea that we have these exponential distance rules laws plus these long-range connections. And it's through these long-range connections that we have this orchestration of the hierarchy of brain function. And that can only really happen on the timescales that are made possible by turbulence. So a long answer to a really difficult question, but I think the exciting thing is that we are again only really at the beginning of trying to understand how that flow is going to change with time. And of course, one of the exciting things is to apply it not just to fMRI, but to MEG, which is one of the things that Kenneth will do in his thesis, for instance.
So full disclosure, Morten is actually my supervisor for my PhD. We'll move on to the next question from Marco. Also for Morten, how does your turbulence approach link to work on brain activity flows in M/EEG? Related question. Does it link to scale-free dynamics we see in M/EEG in the frequency dimension?
So really, I should give that question to you, Kenneth, right? I mean, you've been doing the So we've been doing work on MEG and trying to show exactly these kind of things at different timescales. And it turns out that we can use exactly the same math. Now, the really interesting thing here, and there's a preprint that I haven't put in the actual chat, but which I will put in, and that is one of how these oscillators are interacting. Because you see, the way it works is that you have these Stewart-Landau oscillators. Now, the Stewart-Landau equation is probably the most celebrated in physics. And the cool thing about that is that it can work in what is known as subcritical. So in other words, where you have a bifurcation parameter which is negative at the bifurcation or just below the bifurcation, or supercritical. So in other words, driving at all times. That gives rise to very different kinds of scenarios. You have noise, you have fluctuations, and you have basically oscillations. And really what we've been able to show in this is that the brain works just at the edge of criticality. Not at criticality, but just at the edge of it, because that gives it the maximal amount of flexibility so that one can constantly make these kinds of different coalitions that makes it possible to take in all the information and orchestrate it in the best possible way. And that, of course, is exactly what we can show with MEG. But that's another story and another preprint that I will link.
Amazing. Go to a question from admin team. And his question is, 5-HT2A serotonin receptors are latched onto, 5-HT2A serotonin receptors help the healing process. But if it does not affect dopamine, how effective can this process be in the breaking of addiction cycles linked to dopamine?
So again, this is a really interesting question. Now, one has to think very carefully about what we mean by addiction. So it's very clear that dopamine, of course, plays a role in the wanting mechanisms. So it's well known that if you like something, you also want it most of the time. And when that wanting process, and there's a whole kind of science of the pleasure cycle, which was mainly with my good friend Ken Barrage demonstrated in rats, that you want things, you like them, and then you're satiated and can learn from them. And dopamine, of course, is part of that first process, but it's not the only neurotransmitter involved. In fact, one of the interesting things about addiction and about things like smoking addiction, for instance, I'm sure you all know the data. This is beautiful data coming out of Johns Hopkins from Matt Johnson, showing that if you have somebody who's smoke addicted, you can give them a psychological treatment. And of course, most of the time, it takes about 2 weeks to get into the psychological treatment. And after about 2 weeks after, they stop smoking for a little while, and 2 weeks later, they start smoking again. However, if you give them psilocybin at the beginning of this 2-week period, after 6 months, 80% are no longer smoking. And after a year, 65%. So there are these extraordinary numbers that show that psilocybin together with psychological treatment can basically change the way that you are no longer addicted. And we have reason to believe that it works not just for smoking, but also for things like alcohol and perhaps even for opiate addiction. Now, why does that work? This, I think, is a really interesting question. And one of the exciting things is that Matt has actually collected data from people before they enter into this and after they've been going through this process. And so soon we'll have some answers to that. But I think the easy answer, the sort of hand-wavy kind of answer, is that what happens when you become addicted is that the brain runs in certain cycles, the kinds of control theory that Parker was showing you. Those kind of things change in addiction because of the way that first the patterns change, then the actual underlying connectome changes, and then it becomes very difficult to get out of that rat race, if you like. But intriguingly, it looks as if by actually giving psilocybin, by changing the way that the neurotransmitters are suddenly making it you able to have different traffic on that road map that both Andrea and Parker showed you, that can become permanent. But it also shows you something really interesting about the psychedelic therapies that most of you will know, namely that we can't just give people a psychedelic and expect things to happen. What happens is we see the system, we make the possibility for traffic to flow differently, but then that traffic has to be chained, has to be trained over time. And that, of course, is where psychedelic treatment, so just psychological treatment, can help. But interestingly, and I think very intriguingly, we may also be able to just use music. And that's another story and another thing that we could maybe discuss another time.
Amazing. Andrea and Parker, would you like to share your insights on that question as well?
I think everything that I could have possibly said has been said in better words just right now.
Oh, Parker, I think you're muted.
Yeah, same here. I mean, I might add the idea of de-weighting priors. So it's kind of the psychological aspect of it, more than talking about dopamine in particular, but flattening out that landscape to open up new possibilities. And as Morten mentioned, the kind of entrainment that you need to maintain those new activity patterns. That's all I can add.
Thank you, Parker. Question from Alex, and this is primarily for Parker. Given the numerous interpretations of energy, how many different formalizations of the notion of a free energy landscape of the brain are there? What are the assumptions and implications of each?
That's a tough question. To my knowledge, this work was the first attempt at like actually quantifying this landscape. So and I think Morten hinted at this earlier. I'm not even sure if it was ever really intended to try to quantify, or if it really can be. But you know, what we did here was at least quantify how the structural connectome supports these transitions between different neuronal activation patterns. And this free energy landscape is proposed to hold the state space of these neuronal activity patterns. So, you know, there's numerous things that can in real time change that energy, that free energy landscape. It might be a cognitive demand, or a psychedelic, or, you know, some sort of, I mean, so many things. I think it's really meant to be thought of as dynamic. Yeah, here we just capture a little piece of that, which is how the structural connectome supports these transitions, you know, kind of being agnostic to different cognitive states. I mean, we have the psychedelic state versus placebo, but you know, they're not like doing math problems or something like that. So, yeah.
Alex is saying that this is a question that was also aimed at Morten and Andrea. Do you guys have any insights?
Yeah, so Parker explained very well what the framework of control energy refers to. I just wanted to add a little point that there is actually some work coming out of Danny Bassett's lab, so one of the people who originally formalized a lot of this, showing that there is a relationship between control energy and metabolic energy obtained from PET. So I think more work still needs to be done, but I think those preliminary results are starting to tie together some of these different meanings of energy, and some of their other work has also shown that there is a relationship between control and harmonics. So there might even be a relationship between those kinds of energy. But I need to emphasize that up to this point, the kind of energy that Parker's work refers to and the kind of energy that is referred to in the harmonics work are not the same kinds of energy. It just happens to be a convenient term to use from different branches of physics. But I do think that we will be seeing a convergence, and that we are seeing a convergence in the results.
I think that's a really fantastic answers for both Andrea and Parker. I just want to open up the thing, because of course what we're really talking about here is non-equilibrium dynamics. And really this is what has concerned me over the last 6 months. It turns out that one can describe the thermodynamics of these systems. And of course, that really is the best definition of energy, of production energy, in this case, of entropy. But also one can use the arrow of time to quantify the energy landscape. And there is, again, a preprint under review at the moment that basically formalizes this and gives what I think at this point in time, but of course, I'm always enthusiastic about the latest technology. In fact, remember, technology is a word for something that doesn't quite work yet. But I think that probably is the best way of actually characterizing the energy landscape of any given state in the brain. But yeah, work in progress, exciting times.
Amazing. Question from George, I think also aimed at Parker's research. Have you run this with longitudinal scans after dosing to see if landscape flattening persists, and the extent to which this occurs? This correlates with improvements in well-being. And I guess, just to make that question a bit more general for all the speakers, do you expect to see long-term effects in the measures that you used after people have taken psychedelics?
So I'll start. That's a really great question, George, and one that I would really love to have the data to test. So what I hypothesized that this landscape flattening may have some longitudinal effects. And I tried to look at that the little bit I could with this LSD data set, in which the participants were given either LSD and then 2 weeks later placebo, or the reverse, where they came in first and got placebo and then LSD. And so in our analysis, since we're comparing the landscape of those 2 time points, you could imagine potentially that the people who got LSD at the first time point, or maybe my thing's mirrored. Okay, LSD at the first time point, and then their landscape is lowered. And if there is a longitudinal effect, that maybe it's not as low as the acute. I wouldn't hypothesize that it'd be as low as the acute 2 weeks later, but maybe 2 weeks later, it's not all the way back up to baseline. And the difference in those landscapes might be less than the reverse case, where they got placebo first and then LSD later. I don't think I explained that greatly well. Didn't find significant differences in those 2 groups, but it was trending in the direction that you might expect, where there's some longitudinal flattening. And this is really, I think, going to be a great question when we start to look at trying to quantify this mechanism in patients like treatment-resistant depression who are undergoing psychedelic therapy, where there's so many things going on, potentially longitudinal flattening, but also recovering from depression may have a different effect. So anyways, I'm always all for more data to allow us to ask these questions, but I'll pass it over to you guys.
Since we're running low on time, and I would just like to sneak in one more question, we'll finish with one final question from Alex. To any and all, are you doing any work on / do you know of any work being done on these phenomena in neurodivergent brains, i.e. autism, ADHD, etc.? If so, do any differences arise?
we talking about psychedelics in neurodivergent populations or these measures in neurodivergent populations?
Alex, would you like to unmute and clarify? If not, I'm not sure if she's still here actually. Then I think the question is, oh, she says she's interested in both.
Sorry, no mic. Yeah, so I'm not aware of any data set currently available where psychedelics have been looked at in neurodivergent populations. Most of the work has been done in either patients with either addiction or treatment-resistant depression or in normals. So the answer to that is I don't know. The second answer is, in terms of the neurodivergent populations, we now have quite a few interesting data sets that we've started to look at exactly these kind of measures. And of course, there are differences. One major issue here, though, is how does one define neurodivergent? Because, of course, if you just take something like, say, depression is not just one thing, or schizophrenia is even a better disease. I mean, we have a Chinese menu by which we diagnose these patients. And then it would be strange if we were to find that they all had the same kind of divergence. Because really what we're talking about, as Andrea pointed out, is we have one container with a certain set of connections. And of course, we then have to look at the flow on that manifold. And depending on how that is different, the flow will be very different. So in fact, using these techniques might actually make it possible for us to make a much better distinction about what neurodivergence actually means in neural terms. And once we build a model of it, we may also find a way in which we can change that potentially, or how it is that certain things would bring out the strength in these particular disorders, and perhaps in the sense that it's useful, like in depression, to actually normalize it.
Amazing. Parker or Andrea, would you like to add on to that? All right, great. Well, thank you so much, everybody, for attending. Just a couple notes to wrap up. Our next event is going to be on November 8th. We'll be having a party at the Bullingdon, starting at 6 p.m., followed by some music from an ambient jazz band, as well as 3 DJs. We'll be having some more online events later on in the term. Check out our mailing list for more info on that. Thank you so much again to all of our speakers and our audience for attending. Thank you guys for your questions. All right, see you all very soon. Bye-bye.
Thanks for having us. Bye.
Thank you so much.